Hey everyone, welcome back. Today we're stepping right into the networking lab for a highly technical, but honestly pretty fascinating explainer on the actual backbone of our digital infrastructure. Now, if you're an IT professional, a junior engineer, or a sysadmin, you already know that the OSI model isn't just, theoretical textbook filler. It's absolutely the foundational framework we rely on every single day to design, deploy, and troubleshoot networks. So today, we're going to map physical hardware directly to this model by analyzing three core devices: hubs, switches, and routers. But before we start climbing that OSI stack, I've got to ask you something. Why does device intelligence actually matter in network design? Think about it for a second. We often just plug things in and expect them to magically work. But the reality is, how we handle data flow, literally how smart the hardware is at deciding where a packet goes, dictates our network's overall performance, its efficiency, and ultimately, its ability to scale. If you put the wrong brain in the wrong part of your network, you're going to create massive bottlenecks that absolutely no amount of bandwidth can fix. Okay, let's dive into this. Here is our agenda for today's explainer. First, the OSI hardware hierarchy. Second, Layer 1, the hub. Third, Layer 2, the switch. Fourth, Layer 3, the router. And finally, a head-to-head comparison. All right, Section 1, the OSI hardware hierarchy, scaling intelligence. So the core principle here is that device intelligence scales precisely with ascending OSI model layers. We're going to use a strict bottom-up progression for this explainer. Why? Well, because watching how hardware evolves to solve increasingly complex problems as we move up the stack is by far the best way to deeply understand what these devices are actually doing. Basically, every time we step up a layer, the hardware gains a whole new level of awareness about the data it's handling. Moving right along to Section 2. Layer 1, the hub, the physical layer. Let's start at the absolute base of the model and define the hub strictly by its physical layer boundaries. A hub is essentially just a physical connector. It joins wires coming from different devices, acting as a multi-port repeater. It transmits signals without any processing and, frankly, without any regeneration at all. It operates purely on raw electrical impulses or light signals. There is literally zero software logic happening here. It's just not an intelligent device. So the crucial point is how this complete lack of intelligence actually plays out in reality. Because it operates entirely on Layer 1, a hub works strictly on the basis of broadcasting. When an electrical signal comes into one port, the hub blindly pushes that exact same signal out to every single other available port on the device. It has absolutely no idea who the data is actually for. It's kind of the network equivalent of that one coworker who always clicks reply all. Because they're so simple, they require only a single network, and they're incredibly cheap. Historically, they gave us speeds of about 10 megabits per second, with modern versions hitting 100 megabits, and they're used exclusively in local area networks or LANs. But here's where network engineers run into immediate, real-world problems with hubs. The hub's broadcast to all ports methodology is incredibly noisy. Let's say 10 devices are connected, and device A just wants to talk to device B. Well, devices C through J are still getting hit with all that traffic. This completely eats up bandwidth and causes constant data collisions. We desperately needed a solution to this broadcast noise, which naturally introduces us to a much more intelligent piece of hardware, the switch. Section 3. Layer 2. The switch, the data link layer. Unlike the hub, a switch is a Layer 2 or data link layer, point-to-point telecommunication device. This is where things get vastly better. A switch actually inspects addresses to set up and stop connections exactly as needed. It acts as a kind of bridge, providing way more efficient and targeted connections than a standard hub ever could. So what makes this intelligence tick? Well, operating on Layer 2 means the switch understands MAC addresses. You know, those physical addresses burned right into the network cards of your devices. The switch actively builds a switching table, mapping MAC addresses to specific physical ports. So when a message comes in, the switch looks at the destination MAC address, checks its handy table, and sends the frame only to the port where that specific device lives. This selective transmission effectively reduces network congestion and prevents those absolute nightmare broadcast storms we see with hubs. It features sophisticated flooding, filtering, and frame transmission. Now, while it's more expensive than a hub and still primarily confined to LAN environments, the switch is just a massive upgrade for your local efficiency. Let's move to the next logical step and see how this builds. Switches are incredibly smart for point-to-point local traffic, but they have a hard boundary. They're confined to a single network.
A switch just cannot talk to another, entirely separate network on its own. To break out of the local area network, we need something that understands logical addressing, not just physical addressing.
Which brings us to Section 4. Layer 3, the router, the network layer. Now we're talking about a highly sophisticated Layer 3 device. A router doesn't just connect devices, it connects entire networks together. It utilizes a complex routing table to determine the absolute best possible path between a source network and a destination network. It is the intelligent engine designed specifically to navigate the vast, interconnected webs of the internet and enterprise infrastructure. Because it operates up here on Layer 3, the router doesn't care at all about your physical MAC address. It works strictly on the basis of logical IP addresses. Routers store and maintain IP addresses on their own, allowing them to traverse not just LANs, but metropolitan area networks, or MANs, and wide area networks, or WANs. To even do its job, a router inherently needs at least 2 networks to connect. It performs heavy-duty filtering and packet encapsulation, and because of all this sheer processing power and intelligence, it is naturally the most expensive device of the 3 we're covering today. Speed-wise, we see ranges like 1 to 10 megabits per second for older wireless, up to 100 megabits per standard wired connections. Let's literally walk through the precise routing process just to demonstrate the logic here. Step 1, the router receives data and actively reads the header of the incoming packet. Step 2, it inspects the destination IP address and runs an algorithm against its routing table to find the most efficient path. Step 3, it encapsulates that data and forwards the packet out the specific port that leads to the intended external network. It's literally doing postal service level logistics in milliseconds. All right, Section 5, comparison. Hub, switch, router. And this brilliantly illustrates everything we've talked about. Let's put it all together into an ultimate cheat sheet for your day-to-day network engineering. Notice how beautifully the operational basis scales here. From the hub's blind broadcasting, up to the switch's targeted MAC addresses, right up to the router's global IP addressing. Look at the scope too. Hubs and switches are locked into your LAN, while the router acts as your gateway to the MANs and WANs of the world. Think about it. If you're troubleshooting a broadcast storm, you look at Layer 2. If you're having trouble reaching an external server, you immediately jump to Layer 3. Mastering this matrix is exactly how you efficiently diagnose any network topology. I really want to highlight this quote from our source material. Having knowledge of these differences can become quite important if performance needs to be enhanced for proficient communication of data. For the junior engineers and sysadmins watching this, mastering these layer boundaries isn't just trivia for some certification exam. It is directly tied to optimizing your network's performance. Knowing exactly when to deploy a switch versus when you absolutely need a router is the difference between a sluggish, collision-heavy network and a highly proficient, scalable infrastructure. Which leaves us with this final thought to take back to your own racks and server rooms. Is your network infrastructure utilizing the right layer of intelligence? Are you asking a Layer 2 switch to do a Layer 3 job? Are legacy hubs hiding in a closet somewhere, creating bottlenecks you haven't even noticed yet? Evaluate your hardware stack, trust your OSI fundamentals, and design with intention. Thanks for joining me in the lab today for this explainer, and I'll catch you on the next one.